Oh, maybe I should have connected the Ethernet. Okay. So hi, everybody. Thanks for coming. I'm going to talk about DataBlock studies. And so this is a topic that I think as scientists, we do kind of instinctively, but never or seldom like consciously think about it. And this is the design of experiments, and specifically the design of DataBlock experiments. So first I'm going to talk about the basic theory of design of experiments. And so this is a process that aims to explain a behavior by changing the preconditions and observing the results. So you have some independent variables, some predictors that you're going to change in order to affect the outcomes that you're measuring, and those are your dependent variables. And traditionally, the design of experiments is very hypothesis-driven. So you have an idea of what affects the other thing, and that's how you're determining what predictors to change and what outcomes to measure. And so on a more specific level, this is often done with factorial design of experiments. So this is demonstrated here in this table in the lower right. And so this is an example of testing cake baking. And so you have three predictors that you're going to vary, and you have a high and low option for each of those three predictors. And of course, 2 options for 3 predictors gives you 2 to the third, so you're going to have 8 different runs in order to test all of those predictors independently and also all possible combinations of those predictors. And what that allows you to do is identify which predictors are affecting which outcomes, which predictors work synergistically together or work against each other to affect each of these outcomes. And so, for example, if you look at the high time and the high temperature variables alone, those don't really seem to affect the taste very much. But time and temperature together, if you go with the high option of both, you're going to burn your cake and get a bad taste rating. So this is kind of the most basic example of factorial design of experiments. And it really focuses on validity, reliability, and replicability. So you want to choose your predictors and outcomes that are going to be the most independent predictors. You don't want overlapping predictors, and you want outputs that are going to reduce the measurement error, so things that are going to be repeatable in measurement. You want detailed documentation of your process so that that's going to be reproducible between different researchers, and that your measurements are also reproducible. And then also choosing the number of samples and how you perform measurements for the most statistical power and sensitivity so that your results are statistically relevant. So that's just the basic idea of design of experiments. Again, this is something that I think as scientists you learn to do instinctively, but it's good to know that there is a solid process for thinking about these kinds of things. So then if we talk about degradation science, what we're aiming to do with degradation science is expand from the most basic form of design of experiments, which is encompassed by this traditional reliability part of the schematic here, to incorporate not only accelerated exposures and failures of systems, but also incorporate real-world studies and multi-generational studies to get a true prediction of lifetime performance of a system. So this includes focusing on degradation rates and not failures. So if you think about what does a module manufacturer really want, or what does a power plant really want, they don't necessarily want to see an immediate drive to failure with a single accelerated exposure or a single experiment. They want real world results. And so that's kind of the aim of lifetime and degradation science, is to focus on those rates and the lifetime performance. And so this allows us to cross-correlate the rates with fundamental mechanisms that are causing the degradation, and then develop models for lifetime performance. And so the way this is done is very similar to epidemiology, where we have population-based studies incorporating very large numbers of samples under various conditions, and then correlating the results from those various studies. And this works best with automated field reporting and automated data acquisition, in addition to field survey and things of that nature. And then those are correlated with accelerated exposures. So again, that's incorporating not just the traditional reliability, but also real world studies to then build models incorporating both types of studies that we can build in our own framework for data analysis and acquisition. And so this is all laid out in this paper by Roger French, who's currently participating in Amazon Prime Day, so he's not paying attention. So, but this really lays out the framework of how to design a study in the realm of degradation science. And what that really focuses on is the stress mechanism response framework. So again, it's population-based studies, large numbers of samples, and it also incorporates a number of different levels of the system. So everything from systems to individual devices to materials inside those devices. And then looking at the modes and mechanisms of degradation in terms of the quantitative rates. We employ a number of different exposures and evaluations, and then incorporate those all into degradation pathway network models. And so the way this is all organized is in what we call the degradation science data block for statistical analysis. So this is kind of similar to that table I showed in the beginning, where we had different evaluations and different different outcomes and different predictors that we're changing to determine what's affecting what. But here we have different candidates. So these could be different materials. They could be different materials incorporated into a device or measured on their own, or they could be different systems. And we have different evaluations, and these are really important to consider both performance measures. So this is the end result. What is the ultimate the ultimate determination of success or failure, but then also mechanistic measures. So things like Fourier transform infrared spectroscopy. So for example, if we're measuring a polymer and we're looking at these performance measures like haze and yellowness and microhardness, those things tell us that ultimately, did this fail? Is this failing? What is the performance of the material? But the mechanistic measures tell us what is causing it to fail. And so these are really more diagnostic measures. So something like FTIR, Fourier transform infrared spectroscopy, allows us to recognize which chemical bonds are present in a material. And so as we see certain peaks in an FTIR spectrum increasing or decreasing or disappearing, we can tell what bonds are breaking or forming and figure out what is the problem causing these performance measures to increase or decrease. So in addition to the statistical side of DataBlock studies, we also incorporate a basis in physics and chemistry to incorporate physical models into our study as well. We work with a large and diverse group of samples, diverse exposures, and we also retain samples. And so the idea here is that in addition to our mechanistic and performance-based evaluations, we can also do confirmatory measurements later on, or we can add samples back into our study at various points. And so all of this data is the fundamental basis for correlating this data relies on coincident observations. So we're taking observations of multiple variables at various levels at even and coincident steps during exposure. And so all of this data is incorporated into what we call the energy cradle, which is Common Research Analytics and Data Lifecycle Environment. So here's a schematic of that. So you see here we have input from our real-world experiments, our lab-based experiments, and then from there we're able to store our data, use tools that are common to all of those data types, incorporate physical models and statistical models, and then make a stress mechanism response network to ultimately predict the lifetime of those materials and also make implications for what could be done to improve the lifetime of those materials. So I've talked a lot about stress response and stress mechanism response. And so here are examples of those two types of models. So on the left is the stress response predictive models. And so what we have is a stressor, which is time in this case, cyclic QUV, so alternating heat and light with condensing humidity in the dark. And hot QUV, which is just heat and light. And then our response is a yellowness index. So this is the performance measurement. And so we have a time series of data for 3 different kinds of materials these are different kinds of PET. And so we have that performance over time, and then we're able to build a model and then extend that model to predict future performance past the time of the experiment. But again, telling someone, hey, we know what causes your PET to degrade, it's exposure to the UV. You shouldn't put it outside. And they say, well, I was going to put it on the back of a module, so that's a really unfortunate thing. So while this helps in predicting the behavior of your material, it doesn't really help in helping fix the problem of degradation. And so that's where the stress mechanism response model comes in handy. This uses, of course, a performance metric as a response. So in this case, for a module, our responses are maximum power, fill factor, and then we have stressors of irradiance and temperature and relative humidity. And so if you were to take out the mechanism part of this and make it a stress response model, you say relative humidity causes a degradation in the maximum power point. Well, the implication is then you can't put your modules into any humid environment. And again, that's not helpful. So by incorporating this mechanism, mode response, we're able to measure the hydrolysis of EVA through perhaps Raman spectroscopy. So we get a mechanistic measurement here. We can get a mechanistic measurement of the metallization corrosion through the series resistance of the module, and therefore we can build a stress mechanism response that tells us that relative humidity causes EVA hydrolysis, which causes the release of acetic acid, which causes corrosion of the metal, which then causes degradation of our maximum power point. And therefore, instead of saying relative humidity is bad, we can say what's really bad is EVA hydrolyzing inside our module. We should consider a material besides EVA. And so these stress mechanism response models can change over time as well. So what is your dominant mechanism of degradation in the beginning may change over time. So here, for degradation of an acrylic, we see that it's tinavin bleaching. Tinavin is a light stabilizer, I think. And so that bleaching over time is our first primary mode of degradation. But then we have a change point in our model, and then the mode of degradation changes to chain scission and then mechanical degradation. And so this also brings up the point of why it's so important to have preliminary data or do a preliminary study to determine the appropriate choice of the time step length in a degradation study. Because, for example, if we were to choose too long of a time step, we would only see maybe the second and third modes of degradation. We wouldn't find that first mechanism of degradation. So it's important to make sure that your time step isn't too long, to skip things that are useful to know, but also if our time step is too short, then we're dedicating a lot of time and resources to taking large amounts of data where degradation is not occurring at a significant rate. So finding that sweet spot where your time step is not too long or too short is very important. And so here is an example of a network model for, this is UV stabilized PET. Again, PET is the back sheet on a module, and cyclic QUV is alternating heat and light with condensing humidity in the dark. And so the way this model is built, it uses variables. So here time is our stressor, so it's time in cyclic QUV. We have various mechanistic measurements. So chain scission, crystallization, UV bleaching, and then a performance result, which is here, yellowness index. And the way this is built is that there's a model for each pair of variables. And that model has an associated adjusted R-squared, which also is represented by the thickness or darkness of the line. And so we're able to see that chain scission and crystallization are producing this yellowness in the PET. And so that's just kind of a basic idea of how those work. So this was taken from this study of PET degradation by a former student in our group named Abdul. And so this is his exploratory data analysis of his DataBlock study on PET degradation. So this is what I'm going to spend the rest of the time talking about, is his DataBlock study. So if you think back to the DataBlock I showed, the cube, so these samples are his candidates, so the 3 PET grades. So he has unstabilized PET, UV stabilized PET, and hydrolytically stabilized PET. And so just so everybody's on board, UV stabilized means it has an additive that absorbs UV and dissipates it as heat usually, so that the polymer doesn't absorb UV. And likewise, hydrolytically stabilized is so that the bonds aren't broken by water. And something else to note about these is that they have different thicknesses, so that will come into play depending on the types of measurements that we do on those samples later on. So those samples would be the squares, the vertical squares going back into the page in our DataBlock picture. Here we have 4 different types of accelerated weathering exposures. So continuous UVA, here's that cyclic QUV I mentioned a few times. It's basically the same as the continuous UV, but then alternating with condensing humidity. And then we have constant damp heat, and then alternating damp heat and a freeze. So this is helpful because then we have independent conditions and then alternating conditions that are similar. And then we have 3 different evaluation techniques. So a color, a yellowness index, and a haze, which are all measured with one spectrophotometer. So that's one of our evaluation techniques. And then optical absorbance measurements and Fourier transform reflection measurements. So first, let's look at the raw data. So this is an example of an absorbance spectra. And these are absorbance spectra for UV stabilized PET over 5 exposure steps. So we're seeing that the absorbance is high for the UV, which makes sense if that's what a UV stabilizer is supposed to do. And it's changing over time. So that UV stabilizer is degrading in some way. Then we also have transmittance data. And so these are for the 3 different types of PET. And so one of these doesn't transmit in the UV, and that's our UV stabilized, which makes sense because that one is absorbing there. And then these 2 have a cutoff around 300 nanometers. And this is zoomed in on that region in the lower left. So this is just kind of showing that there are features here, and it's not just a cutoff, a total cutoff in the UV stabilized sample. So then he goes to process the data, and there are a number of things to think about here. One is that the absorbance should be normalized based on thickness. So we had 3 different thicknesses for our 3 different PET sheets. So we should, obviously a thicker one is going to absorb more radiation, so we need to normalize for that. And then a baseline correction in this region where we obviously have absorbance dropping off, but they're not all zeroing at the same place. So baselining spectra. And then the next thing is to calculate the average induced absorbance to dose. So induced absorbance to dose is basically a measure of how much, how the absorbance is changing, what's the rate of change of the absorbance to the total amount of radiation that has been absorbed by the material or has been exposed to the material. And so if it's negative, if it's absorbing less over time, then it's photobleaching. If it's positive, if it's absorbing more over time, then it's photodarkening. And so the next step, now that the spectra are corrected, is to obtain single values. This is really important because if you have spectra changing over time, it's very difficult to build a model for a spectrum changing over time, as opposed to single values, where then you can have how does this peak change from point to point. You have a hard number that you can build a model on. So the yellowness index and haze are already obtained, but then absorbance and FTIR need to have single values extracted. So he chose the fundamental absorption edge that appears at 300 nanometers, a few features with the UV stabilizer that we're seeing here, and the optical density at 400 nanometers related to yellowing. And then from the FTIR, he's choosing various peaks that are known to be associated with chemical species that he knows are in that PET. So the next step is to build the data frame. And so he's got sample and exposure information, the type, the time, step size, irradiation, dose content, etc. The type of exposure condition, and spectral information that's converted to point-in-time measurements. So these are all of the columns he has. So the columns are the various variables, and then the rows are all of the measurements. So he has 90 samples, 30 of each type, and so sample is a factor with 90 levels. He has 405 observations or rows, so those are divided into the sample dash step. So that distinguishes, so one row would contain all of the observations, so all of the various measurements completed on a single sample at a single step. And then some of these are obviously going to be the same for the for multiple rows. Like the thickness is going to be the same for roughly a third of them, because roughly a third of them have the same thickness, and so forth. And then here is where he starts to look at the color index. So lightness, I think this one is red-green, and blue-yellow, yellowness index, haze, etc. And then here we've got observations of the absorbance and the absorbance rate, and then FTIR at various points. So here's what the data structure looks like, or at least the first 8 rows of it. And so at time 0, step 0, none of them have seen any irradiance. And so here at step 6, then this is 1.55 is the irradiance, and then they would make a total irradiance in order to calculate the dosage. So then when we have all of these observations in the data frame, then we can subset the data. So he's subsetting based on the type of PET, so unstabilized, UV stabilized, and hydrolytically stabilized. And then he's further subsetting by the exposure type. There's maybe a simpler way to do this, which I'm not sure he shows. Oh, this is probably the simpler way to do this. Here, we're subsetting by 2 factors, but you can, of course, subset by 2 steps. And so if you wanted a data frame with everything of one type, then that would probably be the best way to do that. And then you can go on to plot. So here he's plotting yellowness index versus time. And then he's fitting it with a line. But this isn't necessarily the most efficient way to go about things, plotting things one at a time. So it's better if we do something like a pairwise plot. And so in a pairwise plot, these are really difficult to understand the first time around, so don't be overwhelmed. I'll explain it. So if you follow the column down from the label, for example, follow time down, everything in this column has time on the x-axis. And similarly, if you follow a variable to the left or right, then it is the y-axis. So you have everything as a function, or you have each pair of variables with the axes flipped. But this is nice to see what correlates well. So for example, time and absorption at 400 nanometers seems to correlate pretty well, whereas haze and absorption at 400 nanometers don't seem to correlate so well. So it's nice to get a first look at this, but there are nicer ways to do this. So this is where it's good to explore various packages open to you. So here is another plot using ggpairs. The ggpairs function, which I think is in, I'd have to look, but it's not in ggplot, but it's in the R Markdown. So go ahead and download the Git repository, and you can look in the R Markdown for this. So here's an example of that. And so here we have density plots for each of these variables, and then we have correlation plots for each of these variables, and then we get a number for the correlation. So that's a little easier to tell what's correlating well. So here we have yellowness index, and absorption at 400 nanometers has a very high correlation value. So another thing you can do is look at the standard deviation, standard error, and confidence interval for these data subsets. So here he's taken all the baseline measurements for each of these 3 types of PET, and then he's calculated the standard deviation, standard error, and the mean for each of those values. So you can see how well, how much those measurements deviate across samples at various steps in your measurement. So he's done that for yellowness index and haze. And then he does some more exploratory data analysis. So here he's got yellowness index for all three types of PET, and comparing those across the 4 exposure types. And so some of these are shown to increase the yellowness index, and some of them are not. So for example, it looks like cyclic QUV and hot QUV are increasing the yellowness index, whereas damp heat and freeze thaw do not. So it would appear that exposure to UV is increasing the yellowness index. And likewise with the haze seems to increase with cyclic QUV, but doesn't change a lot for any of the other 3 exposure types. So here, it may not be UV alone that's causing the haze, but rather the combination of UV exposure and moisture that causes that to occur. So here are his comments. Exploratory data analysis is useful to identify outliers, look for trends and change points in the data, and compare different materials and exposures, and also observe sample and measurement variability. So here he's looking at the change in the absorbance at a particular wavelength across the different exposure types. And so here's a good example of a change point. So he's got a very high change in absorbance at the beginning, and then those don't seem to change very much after the initial time step. Whereas for the absorbance at 400 nanometers, again, the exposure to UV appears to be what's driving those changes, as opposed to the damp heat and freeze thaw, which have little to no change. So again, this is the rate of change of the absorbance as a function of dose. And so since this is negative, it's absorbing less, which means it's photobleaching, but the photobleaching decreases as a function of time. And so these are useful to kind of get an idea of what factors you should be considering when building models and trying to correlate your data. So yeah, let's see. So his conclusions were that light-induced yellowing in light exposure, light induces yellowing in light exposures. So that's what we saw too, was that UV, continuous and cyclic UV are causing that. Moisture-induced hazing, and that it's more detrimental when light and moisture are coupled in the case of hazing. And R is a powerful tool. So what he did from this point, this was kind of a pilot study, was update the number of exposures. So he had a better idea from that exploratory DataBlock study and from the exploratory data analysis on what was causing those particular degradation performance measurements that he was looking at. So from there, he expanded his exposure step to include outdoor exposures, and then also increased his evaluations, but with the knowledge of what was useful and what mechanistically and performance-wise made sense, he was able to further refine this study. Okay, so I think with that, I'll conclude. Thanks.
What was the material that you were discussing for yellow? That was a PET?
Yeah, these are various PETs.
Is that the same kind of plastic that's used on headlights for cars?
I don't think so.
BP would be polyester silicone.
Thanks for calling. I mean, that's the